Hello everyone. On this video we will be covering surface integrals. Alright, so before we get started, just want to take a quick second to remember and kind of give you an idea of where the formula comes from. So if you remember, the formula for an arc length is S equal to the integral from a to b times the square root of x prime squared plus y prime of t squared plus z prime of t squared with respect to t. And of course, it's assuming 3 dimensions. And a line integral that's the integral from a to b f of x of t, y of t, z of t times the square root of your arc length, x prime of t, well, actually times your arc length itself, squared plus y prime of t squared plus z prime of t squared with respect to t. Okay, now this is actually your scalar form of a line integral. But if you were looking for the vector form, that would be the integral from a to b f of x of t, y of t, z of t. Okay, so your gradient times, not your gradient, your vector field times your derivative of your vector function. That's r prime of t dt. Okay, and this is your vector form. All right, so we're going to look at the visual difference between the two, between a line integral and a surface integral. Okay, so line integrals, integrate over a piecewise smooth curve, and actually will probably be more accurate if line integrals were called curve integrals, but the name is the name. Would be better described as curve integrals. But I was not around when they gave out the names, so we're stuck with line integrals. And surface integrals actually integrate over a surface area. Surface integrals integrate over a surface area. All right, so we want to look at a picture of this. Then what we will have, we have our 3 dimensions. So we have our x, our y, and our z. remember that you have your region here. You would find the area over this region using line integrals. Okay. Now let's say if you have yet another three-dimensional area. We have your X, your Y, and your Z. Now let's say here, instead of just a region that's on the XY axis, let's say if you have some sort of curve. Yeah, let me bring that where it's positive. I don't want to go into the negative just for explanation purposes. Try to keep it positive. So we'll go here. Okay, so just imagine you have like I'm trying to get that a better drawing actually. You kind of bring that up just a little bit more. There we go. That may be a little better of an interpretation. There we go. Okay, so let's say you had a curve or a surface area on your XY axis. So imagine if this was maybe like this eraser, where it's not flat, just a flat region, but it's actually an area that comes up. Okay, now this, you'd find the area above that using surface integrals. All right. Okay, so if you are still writing, feel free to press pause, but we're going to go ahead and give the definition for a surface integral. All right, so what if we let our uppercase S be a surface with an equation Z equals G of XY. Okay, and what if we let R be its projection onto the XY plane? Okay, so if our Z equals G of XY and the first partial with respect to X and the first partial with respect to Y, all three are continuous. On that region, and your function f is continuous on the surface. Then the surface integral of f over the surface is, you have the double integral over the surface f of x, y, z with respect to s is equal to the double integral over the region of f of x, y. Instead of z, we're going to make that g of x, y. Times the square root of 1 plus partial with respect to x squared plus the partial with respect to y squared. Get that square root and close it up with respect to the area. All right, now this described a surface that's a function of x and y. You can kind of tweak this a little bit, where if you have, instead of a function on the xy axis, you can have it over the xz or the yz axis also. Plane also. All right, so we're going to show you how that would look if you would tweak it just a little bit. Okay, so for surfaces, here we go. Described by functions of x and z, or in this case, or y and z. Remember, this is for x and y functions. The adjustments can be made. All right, so you can use either one depending on which surface you're looking at. Okay, so first, what if your surface S is the graph y equals g of x, z? Okay, so instead of solving for z, you solve for y. And you make that y a function of x and z. Okay, and we know that your region is its projection onto the xz plane. Okay, so instead of the projection being on the xy plane, as in up here, it's on the xz plane. Then you're going to tweak the formula here just a little bit. Okay, so that means you have the double integral of f of x, y, z, respect to s would equal the double integral over the region of f of x, and instead of y, you're going to put g of xz z times the square root of 1 plus partial g with respect to x squared plus the partial g with respect to z squared. And of course, that's with the area, with respect to the area. Okay. Now also, let's say if the surface is the graph of x equals g of yz. Okay, so it's on the yz plane. And your region is its projection onto the yz plane. Then we tweak it a little bit more. Okay, so in this time, your double integral f of x, y, z, respect to the surface is equal to double integral over the region of f of, and instead of x, it's going to be g of y, z times the square root of 1 plus partial with respect to y squared plus the partial with respect to z squared. Go ahead and close up that square root with respect to the area. All right. So we're going to go ahead and look at our first example. We're going to solve it using two of these. So you can kind of see how you're not just stuck using the xy. You can actually use the yz or the xz. Okay, but usually the xy is a little bit easier. All right, so if you are still writing, feel free to press pause. But we're going to go ahead and move on to our first example. All right, so let's say, for example, what if we wanted to evaluate the surface integral you have y squared plus 2yz with respect to the surface. Okay, and that's where your surface is in the first octant. Is the first octant of the plane 2x plus y. Clean that up a little bit. Plus 2z equals 6. All right, now in some cases they will give you an image, and in some cases they won't. But if you wanted to actually sketch this, it would make it a little bit easier. All right, so if we sketch this, we can actually sketch this using the intercepts. Okay. So if we solve for x, we make y and z equals 0. If we solve for y, we make x and z equals 0. If we want to solve for z, we make x and y equals 0. So if we did that, we would be able to sketch this. Look. Okay, so we have our x, our y, and our z. Okay, so if we made x and y equals 0, we'd end up with the point 0, 0, 3. If we made y and z equals 0, we'd end up at the point 3, 0, 0. And if we made x and z 0, we make this a little bit longer. I'll make that there. We'd be at 0, 6, 0. All right, so how the graph would look, and please forgive my inability to draw yet again. All right, so it would look something like that. All right, let me kind of fill this in a little bit more. All right, so as you can see, the region is not flat on the XY axis. I forgot to put my Y there. Okay, it's actually raised up. All right, so looking at it this way, we're going to look at it on the XY, projecting on the XY plane. All right. Okay, so the first thing you want to do is find z equals g of xy, our first partial with respect to x, and our first partial with respect to y. Because remember, we're using the formula where it's projecting on the xy plane. Projecting on the xy plane. Okay, now mind you, we could also project on the xz plane, or we could project on the yz plane. We're just picking the xy plane. All right, so we have 2x plus y plus 2z equals 6. Now solving for z, that gives us z equals 6 minus 2x minus y over 2. Okay, which means this part right here, that's our g of xy. Because remember, kind of write this over here, z is equal to g of xy when we're looking on the xy plane. So we just solve for z. All right, so we have our z equals g of xy, our partial with respect to x. So we our partial derivative with respect to x is actually just equal to -1. I'll put that over here. And our partial of our g of x with respect to y is equal to -1 half. Okay, so once you find your g of x, well, g of xy, you find the partial with respect to x. So remember, this is a constant, this is a constant, so that would disappear. So that just leaves you -2x over 2. So the partial of that would just be -2 over 2, which is -1. And same thing here. That becomes 1. Those disappear. So we have -1 half. Okay. So now that you have those three, now we go ahead and start plugging it in. Okay, so I'm going to go ahead and rewrite the formula. So we know exactly how we're getting started. Okay, so we want to solve the surface integral of y squared plus 2yz with respect to s. And of course, we're going to use the formula double integral r of f of x, y, and instead of z, we're going to use g of xy. Times the square root of 1 plus partial with respect to x on the xy plane squared plus the partial with respect to y on the xy plane squared with respect to the area. All right, so what does that give us once we get ready to plug it in? All right, so that's going to equal double integral over the region f of xy g of xy. This is our f of xy g of xy, but instead of z, we're going to replace z with our z of xy. Okay, so we have y squared plus 2y, and instead of z, it's going to be times, we can actually get that 6 minus 2x minus y over 2 times the square root of 1 plus partial with respect to x squared, so that's -1 squared, plus partial with respect to y squared, so that would be -1 half squared with respect to a. All right, so actually, this simplifies to actually become square root of 9 over 4, which is 3 over 2. So all of this simplifies to just 3 over 2. All right, so we're kind of jumping ahead a little bit. Okay, so these two will cancel out. So we end up with double integral over the region of y squared plus y times 6 minus 2x minus y times 3 over 2 with respect to the area. Okay, so now we just go ahead and simplify this. So, there we go. Close that up. So if we go ahead and simplify this by distributing and multiplying and all that good stuff, we end up with the double integral over the region of 9y minus 3xy with respect to the area. All right, now this next part is where the image comes in handy. Okay, so because we're looking at the xy plane, we're going to graph just like this little triangle here on the xy plane. Okay, so we know on the x-axis it goes from 0 to 3, and on the y-axis it goes from 0 to 6. All right, so just go ahead and jot that down. Okay, so from the surface, okay, so we see here, we have our x and we have our y. Remember, this is 0, 6, 0 and 0, or 3, 0, 0. Oops, missed my line there. I'll just move that over a little. So 0, 6, 0 and 3, 0, 0. Okay. So now what we have to do is we have to find our, I guess you could say, your equation here. All right. So if you remember, your slope is y2 minus y1 over x2 minus x1, which is 6 minus 0 divided by 0 minus 3. 6 minus 0, 0 minus 3, which is negative 2. Okay, and our y-intercept is 0, 6. Okay, so really that would give us the equation y equals negative 2x plus 6. All right, so this gives us part of our region. Okay, because we can't just say that y goes from 0 to 6 because it goes at that angle, so we have to put in that equation. It's not like it's just a straight line 6. Excuse me. All right, so we're going to go ahead and plug this, using this formula here, we're going to plug in our region. Okay, so we have our double integral. I give it a little bit of space. We have 9y minus 3xy. With respect to y, with respect to x, you can do yx or xy, doesn't matter. But because we have our y formula here, we'll do the y first, and this way we can just plug in the x and solve for the values. Okay, so this is from y equals 0, since we're doing the y inside first, to y equals negative 2x plus 6. And then, of course, the x is just going from 0 to 3. Yep, clean up that 3 a little bit. All right, so just like always, we're going to start integrating from the inside out. Move that over a little. Okay, so that equals the integral from 0 to 3, 9y, y squared over 2. So that's 9 over 2y squared minus, with respect to y squared over 2. So that's 3 over 2 xy squared. And remember, that's from y equals 0 to y equals negative 2x plus 6. All right, so I'm just going to move that equal over a little bit. So that's equal to the integral from 0 to 3. Of course, plugging in y equals 0 is just going to be 0, so really we just have to do the top one. So we have 9 over 2 times negative 2x plus 6 squared minus 3 over 2x times negative 2x plus 6 squared with respect to x. Okay, so once we square that out, we FOIL it, and we do the same thing here. We square this, and we FOIL it, and we do all of our distributing and combining and everything else. So in other words, after a bunch of algebraic manipulation, okay, so after a whole bunch of algebraic manipulation, you end up with, move that up a little bit, say negative 6 times the integral from 0 to 3 of x to the third minus 9x squared plus 27x minus 27 with respect to x. All right. Now we're running out of room, so we're going to actually continue this on the next page. All right, so if you are still writing, feel free to press pause, but we're going to go ahead and move this one on to the next one, next page. All right, so if we continue here, remember we started off with negative 6 times the integral from 0 to 3 of x to the third minus 9x squared plus 27x minus 27 with respect to x. All right, so if we go ahead and integrate each one of those terms, that's negative 6 times x to the fourth over 4, or 1/4 x to the fourth, minus x to the third over 3, the 9 and 3 cancel, so that's 3x to the third, plus 27 over 2x squared minus 27x, and remember that's from 0 to 3. X equals 0 to 3. All right, so if we go ahead and plug in our 3, because of course once we plug in the zeros, it's just all going to be 0. We have negative 6 times, that should be 81 over 4, since 3 to the fourth power is 81, minus 81, plus 243 over 2 minus 81. All right, so kind of just adding and subtracting fractions from here on out. So we have 81 over 4 minus 324 over 4 plus 486 over 4 minus 324 over 4, which is equal to negative 6 times negative 81 over 4, which is 486 over 4, which simplifies to 243 over 2. All right, so that's our area. Excuse me. Okay, so that's when we get it reprojected over the xy plane. But what if we wanted to project it over a different plane? Okay, so I'm going to do the exact same problem, but ask the question, what if we project it, projected S onto the YZ plane. Okay. Now, if we project it over the YZ plane, we still start off with our 2x plus y plus 2z equals 6. But since we're projecting over the YZ plane, we solve this for x. So x is equal to 6 minus y minus 2z over 2, which means this is our g of yz. Okay. Now find the partial of this with respect to y is negative 1/2. And the partial of this with respect to z is equal to negative 1. All right, so if you go back to the previous page, I'm going to cover this up just for a hot second. We're going to look at now the YZ plane. Okay, so we're looking at it. So what we're going to do, we're going to go ahead and graph this. Okay, so if we graph this, and instead of x and y, this is y and this is z. Remember, y means z goes to 0, 0, 3. And y is 0, 6, 0. Here we go. So that means we want to find our formula. And that slope is going to equal z2 minus z1 over y2 minus y1, which is 3 minus 0 over 0 minus 6, which is negative 1/2. And the z-intercept, remember that's yz, is equal to 0, 3. Okay, so using those two, we can come up with our equation. Z is equal to negative 1/2 y plus 3. Okay, so remember, this is what we're going to use for our region. All right, so now going up, we start off with the same formula we want to same problem we want to evaluate, to yz with respect to s. Remember, that's going to equal the double integral over the region. And clean up that r. Of f of, instead of x, is g of y, z, y, and z, times the square root of 1 plus the partial with respect to y squared plus the partial of g with respect to z squared with respect to the area. All right. The thing is, once we plug in our partial with respect to y, partial with respect to z, this, once again, just equals 3 over 2. We're going to kind of skip ahead on this one a little bit, since the steps are pretty much the same. Okay, so that gives us, remember, y goes from 0 to 6, but we're going to put that down first. First you have y squared plus 2. You have yz. You don't have to replace x with anything. So in this case, this stays 2yz times the square root. That just becomes 3 over 2 with respect to z with respect to y. And remember, z goes from 0 to negative 1/2 y plus 3. And y goes from 0 to 6. Okay, so we're going to kind of distribute and everything else there, but after we integrate, since we're kind of running out of room, you have 3 over 8. After integration, 3 over 8 from 0 to 6, 36y minus y cubed with respect to y. So again, this is after you integrated this with respect to z. So we're just kind of jumping ahead a little bit. And the reason why is because once you integrate this, you just end up with the same answer of 243 over 2. Okay, so I didn't want to burn a whole lot of time doing the exact same steps to get the exact same answer. This is just to show you that if you did do that, you would end up with the exact same answer. Okay, so you wouldn't have to go through the same steps that we just did because we did it already once, so there's no point in doing it again. All right, so if you are still writing, feel free to press pause, but we're going to go ahead and move on to our next page. Okay, now this one talks about the orientation of a surface. All right. Okay, now what we mean by orientation breaks down to just this. A surface that, of course, we usually call S is orientable if a normal vector. Now, normally, when we describe a normal vector, it's a lowercase n. You can use either a lowercase n or an uppercase n. It doesn't matter. I'm just switching it up to an uppercase n here. But if you're more comfortable with the lowercase n, you can use the lowercase n if you like. Okay, I'm just using the uppercase, and you'll see why I'm using the uppercase for the orientation, and I'll show you that in a second. Okay, so the vector can be defined at every non-boundary point of your surface. That, of course, we will call S, such that the normal vectors vary continuously. That means they change over the surface. So the normal vectors vary continuously over the surface. Oh, well, might as well put the S there. Okay, so if this happens, this actually creates what we call an oriented surface. This creates an oriented surface. All right, so this is kind of the written description of it. To give you a visual description, we kind of separate that a little. So visually, okay. Let's say when z is g of x, y, we know that if we subtract g of x, y from both sides, z minus g of x, y is equal to 0. Okay, so this, we will actually give that its own definition, which is an uppercase G of x, y. Okay, so that's why I use the uppercase normal vector for our uppercase G of x, y. All right, so if we draw our three-dimensional area here, Okay, so if we have our x, our y, and our z-axis, now let's say if we have some area in, not some area, some surface in space. Okay, so if we have some surface kind of just floating around in space here. Okay, so this is what we will call our surface S. Let's say in that surface, we have that little area. And in that area, you have your normal vector off that point. Okay, we know our normal vector is equal to the gradient of G. Clean up that G a little. So you have the gradient. Okay, just did it again. The gradient of our uppercase G, there we go, over the magnitude of the gradient of our uppercase G, or G of x, y. Okay. Now in this case, we know that our surface is oriented upward. Okay. Now if it's oriented upward, we know that our normal vector is equal to the gradient of G over the magnitude of the gradient. Which is equal to negative G with respect to x, or the partial derivative of G with respect to x, and I, minus partial with respect to y times the J unit vector plus the K unit vector divided by the gradient, which is the square root of 1 plus the partial with respect to x plus the partial with respect to y. There we go. Okay, so this, you're oriented upward. All right, now if it's oriented downward, it's just a minor change to it. Really, it's just the negative of your unit normal vector. All right. Okay, so let's say for our downward oriented surface, again, we'll draw our three-dimensional area. So we have our x, our y, and our z. Okay, so let's say if we have that very same surface that's just kind of floating in space there. And let's say that area there, and this is, of course, our surface here. So if we get one little area of that surface, if we're on the inside, that surface is going to, well, that normal vector is going to point down. Okay, so this will now be the negative of your gradient over the magnitude of the gradient. So once again, it just switches up just a little bit. Okay, so you have the negative of your gradient over the magnitude of your gradient, which is equal to the partial with respect to x times the I unit vector plus the partial with respect to y times the J unit vector minus the K unit vector, all over the same magnitude, which is 1 plus partial with respect to x plus the partial with respect to y. And go ahead and finish up that square root. Okay, and this is how you know that your surface is oriented downward. All right. Okay, so if you are still writing, feel free to press pause. But we're going to go ahead and move on to our next page. We're going to continue this actually on our next page. Okay. Okay, so let's say if the smooth surface S is in parametric form, let's say R is a parametric function of U and V. Those are just kind of dummy, we call those dummy variables, U and V. Okay, so that's X of U and V times the I unit vector plus Y of U and V times the J unit vector plus Z of UV times the K unit vector. And that means your new unit normal vector again, we're using the uppercase N. If you want to use lowercase n, you can. That's going to equal our vector function, or the partial of our vector function with respect to u, and the cross product of our vector function with respect to v over the magnitude of it. Okay, or you could switch it up. Okay, over the magnitude of that cross product. All right, so just like before, you can switch it up based on which plane you want to have your projection over. Okay, so if, let's say, you want to solve for y instead of z. Or if you want to solve for x. Then that means your gradient is going to be negative partial with respect to x plus j, your j vector, minus partial with respect to z times your k unit vector. Okay, so if you notice before, when you solve for z, there was nothing next to the k vector. But here, when you solve for y, there's nothing next to the j vector. But that's assuming that g of x, y, z is y minus g of xz. All right. Okay, now it's the same thing if you solve for x. Okay, so that would equal I vector minus partial with respect to y times the j unit vector minus the partial with respect to z of the k-unit vector. Of course, that's when g of x, y, z is equal to x minus g of yz. Okay, which leads us to our parametric surface integrals. Parametric surface integrals. Okay, so we have the double integral f of x, y, z with respect to the surface. That's going to equal the double integral of our domain of f of x uv, y uv, and z uv times the magnitude of our cross product. Okay, so the partial with respect to u and the partial with respect to v with respect to the area. All right, and of course, that's when your surface is a vector valued function. So you have x of u v times the I vector plus y of u v times the j unit vector plus z uv times your k unit vector. All right. So if you are still writing, feel free to press pause, but we're going to go ahead and jump to our example. All right. Okay, so let's say, for example, if we wanted to evaluate our double integral of f of x, y with respect to s, where our f of x, y is equal to xy, and our surface is the vector function two cosine of u times the I unit vector plus 2 sine of u times the j unit vector plus v times the k unit vector over the integral between, we'll use between 0 and pi over 2, and v is between 0 and 2. All right. All right, so we're going to go ahead and solve this one. Okay, so first we're going to go ahead and write down our surface. Okay, so you have 2 cosine of u times the I unit vector plus 2 sine of u times the j unit vector plus v times our k unit vector. All right. Now we know here this is our x of uv. This is our y of uv. And this is our z of uv. Okay. So now we have to find the first partial derivative with respect to u. Okay, so the derivative of cosine is negative sine, so that's negative 2 sine of u times the I unit vector. The derivative of sine is cosine, so that's plus 2 cosine of u times the j unit vector. And because it's with respect to u, that v is a constant, so that just becomes 0. So you can actually write plus 0 times the k unit vector, just as a placeholder. All right, so now we find the partial with respect to v. Okay. This is a u function, u term, so that's treated as a constant. That disappears. Same here, that disappears. So you have 0i plus 0j. Partial with respect to v of v, that just becomes 1, so that's plus. You can put 1k or just k. Doesn't matter. Okay, so now we find the cross product of those two. Okay, so our cross product, okay, if you remember, I'm running out of pencil lead here. There we go. If you remember for the cross product, your first row is your I, your J, and move that, give it a little more room, and your K. Your second row is your partial with respect to U, so that's negative 2 sine of U, 2 cosine U, and 0. And our third row is our partial with respect to V, which is 0, 0, 1. Okay, now if you remember, it's plus, minus, plus, or positive, negative, positive. Okay, so that's going to equal, remember you cross out the I, or the I column. Okay, so you have 2 cosine of U times 1, which is 2 cosine of U, minus 0 times 0. So that's just minus 0 times the I unit vector. Remember, positive, negative, positive. So we have plus, minus. Cross out the J column. Negative 2 cosine, negative 2 sine of U times 1, which is negative 2 sine of U, minus 0 times 0, so that's 0. Plus, cross out the K column, you have negative 2 sine of U times 0, which is 0, and 2 cosine of U times 0, which is 0. So we have 0 minus 0 times the K unit vector. Okay, so we know that our cross product is equal to 2 cosine U times the I unit vector plus 2 sine U times the J unit vector. Okay. You don't have to put the K since it's 0K, and I'll show you why. Because when you find the magnitude of the cross product, that's just equal to the square root of the first term. So that's 2 cosine of U squared plus 2 sine of U squared. Didn't need that to be so far out. Okay, which ends up being the square root of 4 times cosine squared U plus sine squared U. And we know that this is just going to be equal 1. Cosine squared and sine squared is 1. So that leaves you the square root of 4, which is 2. All right. So now we're going to go ahead and plug that into the formula to evaluate our function or our integral. Okay, so that means the double integral over the surface, your f of xy, remember that's just x times y. So we're just going to go ahead and plug that in. So you have xy with respect to s is equal to double integral of your, remember, f of x uv y uv. So I have 2 cosine u, 2 sine u times 2 respect to u with respect to v. All right, now looking closely at this, this is our x equals x of u v. Remember, we identified those earlier. That's our x of u v. This is our y of u v. Okay, and remember this is our magnitude of our cross product. Okay, so if we go back to the previous page just for a second, you'll see we covered everything that we need. All right, so this is the formula here. Function x of uv, y of uv, z of uv, and our magnitude. All right, so now if we go from the inside out, we know that our u, which is already identified, goes from 0 to pi over 2, and our v goes from 0 to 2. All right, so if we go ahead and integrate the inside with respect to u, we have the integral from 0 to 2. And remember, using our u substitution, that's where that will come in. So we end up with 8 over 2 sine squared u from 0 to pi over 2. Oh, and forgot our dv. Okay. So we know that sine of pi over 2 is equal to 1. So that really just leaves us with 8 over 2 times 1, which is just 4. And 0, you plug in the 0, that's just 0. So that leaves us with the integral from 0 to 2 of 4 with respect to v. Okay, so that gives us 4v from 0 to 2. Plug in the 2. You have 4 times 2 minus 4 times 0, of course, is 0, which is 8. All right. So that is how you would evaluate for your vector, your parametric surface integral. Okay. All right. So hopefully this one made sense. We're actually going to continue this on a second video because I didn't want to make just one humongously long video. So we're kind of breaking this down. So we're going to continue on the next video. So I will see you then.